All right. Good morning. Good morning. This is gonna be my third attempted stream. Hopefully, my settings have been working. If not, then we just gonna keep trying till it does. Um, this morning we're not gonna do nothing too intensive. I started leak coding as a daily practice for about 2 weeks ago now. And so I am going to use these streams just for now as just a review type thing. So I remember different algo patterns and whatnot. And then after that, I'm going to get started on my actual work. And so for this one, let's see. Let's see. I go neat code. That's right here. Roommate. So, um, let's go with combination sum. So, let's see where I got this one. I think this one is something I did not solve. Wait, did I? I don't remember my last solved solution actually that I recorded. Um, Whatever. Combination sum. You are given an array of distinct integers, nums, and a target integer target. Your task is to return all unique combinations of num where the chosen numbers sum to target. So through these nums, we get we make little subarrays till we get target. And so you can use the same number multiple times. Two combinations are the same if the frequency of each of the chosen numbers is the same, otherwise they are different. You may return the combinations in any order, and order the numbers in each combination can be in any order. So, oh, I should probably use that thing Bite Size told me about. Umpire solving method. Is it umpire? Oh shit. What did Bite Size tell me it's called? Fuck. Shit. Problem solving. No, I think it is umpire. Yeah. Hey, bro. Amen. Why don't you just tell me what it stands for, motherfucker? Understand the problem. How is P defined test case? Come on, come on. Understand, match, plan, implement, review, and evaluate. Oh yeah. I also um let's see. In my Obsidian, I have been starting to take actual notes and logging the different questions I've been attempting. But for the earlier ones, I did not do that, so I'm gonna go ahead and start doing that. So this one is called uh, combination target sum. All right, so this one's called combination target sum. So let's go add that. Combination target sum. All right, and then we want this. All right. So oh fuck, I didn't gotta use umpire. Let's see, how does this work? Understand what the interview is asking for by asking test cases and questions about the problem. I think I understand it pretty well. It's not probably not the way you're supposed to say it. Um, so we're returning a list filled with subarrays that contain different ways that a target number can be reached. From in those subarrays, they can be derived from the nums array, in which we can use any amount of we can use the indices inside of them as much as we want, unlimited times until a target is reached. However, a subarray is considered the same depending on the frequency of numbers inside each subarray. So 225 will be the same as 522, and so on. So that means they can be in any order as long as the frequency of each chosen number is the same. And then I think that's about it. Match what the problem looks like to other known categories of problems. This is a backtracking problem. I know this because it was in the roadmap, but also we can say that it is backtracking since we are testing a bunch of different combinations to reach some desired goal. So I guess that's a task better suited for depth research. I'm not too completely confident in any other way that can complete something like that. Plan the solution with appropriate visualizations and pseudocode. Now this would be helpful because it's been a while since I did this, so let's try to draw it out. Why is this in dark mode? Make this black, please. Thank you. So let's see how we can do this. We are given an array of 2, 5, 6, 9, 2, 5, 6, and 9, and a target, right? And we can start with an empty array at the beginning of our traversal, and we can start here. And knowing that, okay, so this probably comes back to the understanding part of umpire, but I want to know if numbers will be repeated in our nums array. Distinct integers, so they won't be repeated, which is good. So we don't have to account for duplicates. Another thing, so since we don't have to account for duplicates, we can just traverse left from right, knowing that each indice will be unique. So we can traverse left from right, and we can keep track of a target. And so from the left, we'll add 2 here, right? And then that means our target right now, or we can either track a target where we take a parameter target, which is 9, I think, and we keep subtracting whatever indice we're using until we reach 0. So at this point, it'll be 9 minus 2, which will give us 7 or whatever. And then once it reaches 0, then we know that, hey, yo, this is a perfect subarray, right? But I think I think I tried that method when I was solving this either a week ago or 2 weeks ago. And I think an easier way is just adding until you reach 9. It's pretty much the same thing. But yeah, I'm just going to do adding. So our target now is 2. And over here, we're not adding anything, so that in this branch, it can start with 5, right? And so in this way, we can keep completing this. So once these 2 choices are done, we can try looking into the next indice to see if we can add or not. And so for some reason I can't pan or zoom out, which is annoying. All right. And so we can keep going, and this time we're at 5. And so we can go ahead and add 5. So this would be 2, 5, giving us 7, right? Oh, you know what? Since we can reuse it a lot of times, this is not a good approach, because we have to account for that 2 can keep being reused. So it can go ahead and be go ahead and be 2, 2, and then 2, 2, 2, and then 2, 2, 2, 2, right? And so this is 8, and then it'll hit 2, 2, 2, 2, 2, which is not 10, which is greater than what our target is. So this will give us a return with nothing added. And so we have to pop this recursively so that once we're up here, we can go ahead and go here and try the next indice, 8. And then this is where an optimization can come in. We know that we know that where our target is 9 and we're currently at a total of 8. So if the difference between that is greater than the current number we are on, if this array is sorted, so it's probably smart to sort this array. If this number is sorted, then we can go ahead and say that we don't need to look into this branch any further, since everything above than 2, so we gotta sort as well. Anything above than 2 will be considered, will overflow than what will be greater than what our target is. Jeez, I really had to fight for that fucking, okay. Yeah. 2, 2, 2, so we know that that won't work. 2, 2, 2, we're at a total of 6, right? And so 4, as long as it's greater than 4, we can keep trying other indices. This one is 5, right? So at 5, it probably won't work. Yeah. So now we're at 2, 2. This is giving us 4. We know that 2, 2, 5 will work. 2, 2, 5. And that will be our first sub array that we append, right? Since it's 2, 2, 5, I guess we can return. And then since we return, we can try anything greater than 5 won't work, right? So I guess we can go back up 1. And that gives us the question, if the target was, I think that works there. 2, 2, 5. Yeah. So I guess we have a rough idea. So we keep appending our this indice until it overflows or it reaches the target, and then as we recursively backtrack, we can try different indices to see with these combinations to see if it will give us a combination that will work. There is some optimizations that we need to do so that it doesn't go into useless trees, right? But for the most part, hopefully we can get all the combinations for this. This one's 2, 2, 5. A sort would be helpful because with a sort, we know that when we reach a certain configuration, we can stop the backtracking earlier, because we know that looking through the indices would be pointless because all the numbers will be greater. One thing that I did not look into is how we are going to handle things that don't start with two. So let's say since the two branches is done over here, we'll start with the fives, right? If we are starting with the fives, we are not going to use any of the twos. And the reason is any combination of five that works with the twos should be completed in this tree, right? Now, my question is if we go ahead and say to in this left tree here, um will it work if we have a combination of like our target is 10, right? So the way this would work is we would get 222 as a subarray. 222, this would give us 6, right? 6. Oh wait, this would give us 8. Nothing in there. This will give us 6. Nothing will work. But over here, my question is, will this algorithm give us a combination of 255, right? So a duplicate of the second number. Because if we aren't going to allow twos to be accessed in this right branch, we want to know that 255 solutions with repeated fives will be able to be found. So sorry, it's really early. This explanation is slow. And so we are going to go 255. So at 2, we are going to do 2. Oh yeah, for sure it will work because it will just keep appending the current indice until its target. Yeah, so even if we're on another indices, we keep appending that indice. And so the plan is we are going to sort so that we can do it. Keep appending current indice, and then keep. That's not how you spell it. Appendice. What the fuck? Index. Keep track of total. If total equal target, append subarray to global answer array, and then if total is greater than target, we want to return, which will be one of our recursive cases. And then if total is less than target, keep appending current index. Now we want to check if the difference, if target minus total is less than so if the difference is less than our current index, so nums of index, we want to stop backtracking, because that's where the optimizations come in. Like if we know that we're at 8 here and the target is 9, that difference will be 1. And so if we're currently at 2, no matter how much we look to the right, if our array is already sorted, we know that we won't ever reach a number that will find us a target combination. The other case is we have completed iterating, like we kept adding our 2s, right? But then we overflow, right? So in this case, we're looking at a target of 9. And we overflow, we get a 10. So we go back 1. And once we go back 1, difference is too small, so we go back again. And then here we have an opportunity to branch out with the next index. So we can say while backtracking, Branch. I guess this can be an else while backtracking. Branch with the next indice. So in our depth first search, we are incrementing indice by that. And then we can go ahead and say that we have an answer. And then a total sum will probably be kept in our depth first search. Shit, what the fuck? Total can be kept in our depth first search where we are keeping track of index, subarrays, and total. Right, and then we pass, and then we have our base cases we gotta define, and then we have our recursive calls, and we need to do, I think sorting things is like this, or is it sorted? What is the diff? I think one returns a string and the other just changes it in place. Can't give me a quick synopsis, man. All right, here it is. In place, sort is in place, sorted returns a sorted object, and it's probably best if we do in place for now. I think. Sure. Or we can do nums equal nums dot sort, right? We'll see. So it'll look like this, right? Cases. And then we need to call our depth first search on the first index of an empty subarray with a total of 0. And then we know that if total is greater than target, we need to return if target. So this is trying to optimize position attempt. So if target is greater, if target minus nums of I is greater than, oh, we also want to say if our index is greater than or equal to, well, it's probably never going to get greater than, what the fuck? It's probably never get greater than, but if it's equal to the len of list, which is, so we can add that here. Or if index reaches the end. So that pretty much just means we are visiting every little node in our array, and if it reaches down here, that means we are done, you know? Yeah. And then optimization, if the difference is greater than our current one, so nums of I, if it's less than, actually, this might be wrong. I can see it going wrong. Every time I try to optimize early before getting like a normal brute force way down, it usually goes wrong. So we understood, we try to match it. We're planning a solution. We are implementing it now. Review and then evaluate. God damn, this method is long, bro. I usually just start typing, dude. Okay. So now that we did this, it's not break as return. This can also be added up here. So to optimize the code, we can probably to make it shorter, we can add it up there. Recursive calls. So we want to append our, so index stays the same, right? And so we're gonna do subarray dot append our nums at index. So now we are finally adding to the subarray, right? And that's only if if target plus nums of index is less than or equal to, and then we also got to do if total equals target, then we want to return our, no, we want to append our subarray. Yeah, we want to append our subarray and then return. So a lot of base cases I need to combine later on, but that's kind of where I'm at right now. And then we want to make sure that append it, def first search, and then we gotta pop it, right? If I'm thinking about this correctly. And then here our index will be incremented by 1 plus 1, and then it's going to be the same subarray that's unchanged. Subarray. And then total is total plus nums of index. Nums of index plus 1. Like that. This may be wrong actually, and then we gotta turn answer. All right. Review. Run specific examples. Let's just see how I did it last time. I did it August 21st. Damn, I did this a while ago. Okay. Kept global. I didn't sort it though. Interesting. If local total, so I did that. If it equals target, we append it. Oh shit. This way is way easier. It was way easier. So I went through the array. So instead of moving index through the parameter, like I'm incrementing it here, I just did it in a for loop. Yeah. Well, I guess that works. How did this guy do it? So keep a result. I guess it was pretty fucking pointless for me to sort, bro. Okay, whatever. So same thing. Total is greater, same thing. I guess there's no point in optimizing it. Oh, and this way is how, okay, so it's pretty much the same shit. Yeah, it's pretty much the same shit. The only difference is he appended nums of index, and then he did the current index. What is cur? Cur, oh, it's his subarray. And then total plus nums of I. Yep. And he got rid of it, and he just calculated the total, which makes sense. So that was an oversight on my part. All right. All right. So I just did it a step too early. This information will be calculated here. We just want to make sure that when we are backtracking, everything is set back to normal, which is why we pop and then we run that. I think pretty good though. Review the code. Evaluate the performance of the algorithm. So this is a def first search algorithm, which means it is recursive. Well, it's implemented recursively. And so I know that usually with recursive problems, there's like a rule for every recursive call that's like the base. and then it's to the power of n. And so since there's two recursive calls, I guess it's 2n. Is that right? I'm real bad at fucking figuring this cool stuff out. What do you say?
Hey everyone, well,
Do you write it out?
second time. So we did create two branch decision. Return that result.
I think I am right. Or am I wrong? Who knows?
Contain all of the combinations. Please like and subscribe. So I hope that this will link to the target. So you can 0 as the current total. So we can choose. Let me show you how to do that. It's going to be a base case.
Yo, O of n. I mean 2 of n. Fuck. Alrighty. That's a good review. I just gotta make sure to be careful with this. And this was a waste of time, and this was a waste of time. So, oopsies. Yeah. So I'm gonna stop the recording. Hopefully it worked out. I'm gonna stop right now and actually get on to some work that I've been putting off. But yeah.